Hey guys, today I want to present a solution to the International Math Olympiad 2011 problem 4. At first, let's have a look on the problem statement. We are given the n weights 2 to the power of 0, 2 to the power of 1, and so on up to the weight 2 to the power of n minus 1. And now we want to place them one after another onto a balance in such a way that the total weight on the right pen is never heavier than the total weight on the left pen. Now our task is to determine the number of ways, I call it f of n, in which we can do this. At first I want to make an example to make the problem statement more clear. So let n be equal to 4, and then we have the weights 1, 2, 4 and 8. So now we have given the balance, and now we want to place these weights onto the balance. And for example, we can start with the weight 2, and we have to place the weight 2 onto the left hand side, because if we place it onto the right hand side, then the right hand side is heavier. Now we can, for example, choose the weight 4, and now we have also to place the weight 4 onto the left hand side, because if we place it to the right hand side, then the right hand side is 4 and the left hand side is 2, which is not allowed. In the next step, we can choose the weight 1, and here we can place it on both sides, because 1 is less than 2 plus 4, which is equal to 6, and therefore if you place it onto the right hand side, it is allowed. In the last step, we have to choose 8, and here we have to put 8 onto the left hand side, because if we would put it onto the right hand side, we have 8 plus 1, which is equal to 9 on the right hand side, and 2 plus 4 on the left hand side, and this is not allowed. So we have to place 8 onto the left hand side. So this is one example how we can place the weights onto the balance for n equals 4. From this example, we can directly see a pattern in the problem. Namely, that the heaviest weight on the balance is always heavier than the sum of all the other weights, since we deal with powers of 2. And this means that the left pen is always heavier than the right one. In particular, after the first step, equality cannot hold anymore. And therefore, if we place the weight 1 after the first step, we have always both possibilities to place the weight 1 onto the left hand side or to place it onto the right hand side. On the other hand, if we place the weight 1 in our first step, then we must obviously place it onto the left pen. This is already a really nice observation, and therefore I want to write it down. So now, with this observation, we can totally count the number of ways to place our weight 1. So at first we have the first case, that we place the weight 1 in the first step, and here we must place the weight onto the left pen. Therefore, there is one way. On the other hand, if we place the weight 1 in every other step, we observe that we can place it on both of the pens. So we can place it either on the left pen or on the right pen. Since there are n steps in total, we have here n minus 1 possible steps, and since we can place in every step here the weight 1 onto an arbitrary pen, we have 2 times n minus 1 ways. So in addition, we have 1 plus 2n minus 1, which is equal to 2n minus 1 ways to place the weight 1. Now recall that only the heaviest weight on the pen at every point is relevant, since his weight is greater than the sum of the weights lower than it. This means especially that our weight 1 has no impact onto the placements of the other weights. So consider the weights from 2, then 2 to the power of 2, and so on, up to the weight 2 to the power of n minus 1. Now we can have a look on how many ways there are to place these weights onto the pen. And for every way here, and for every way to place the weight 1, we get a way to place these weights here from 2 to the power of 0 up to 2 to the power of n minus 1. And we also get the other way around, so we get from a placement of these weights here, one way to place the weight 1, and the way to place the weights here. Thus, there exists a one-to-one correspondence between the number of ways to place these weights here and the number of ways to place the weight 1 combined with the number of ways to place the weights 2 up to 2 to the power of n minus 1. Thus, if f of n is the number of ways to place the weights 2 to the power of 0 up to 2 to the power of n minus 1, we get that this is equal to the number of ways to place the weight 1, which is 2n minus 1, times the number of ways to place the weights 2 up to 2 to the power of n minus 1. But now it is irrelevant if we deal with these weights or divide all the weights by 2. And then we come up with the weights 1 up to the weight 2 to the power of n minus 2. And this is exactly the number of ways to place here the weights 2 to the power of 0 up to 2 to the power of n minus 2. So this is exactly f of n minus 1. But now we can go on with the same idea and say that this is equal to 2n minus 1 times 2n minus 1, which is 2n minus 3. And now we have a f of n minus 2, but we can repeat this process and end up that we have here r times 2n minus 5 and so on up to f of 1. But now f of 1 is nothing but the ways to place only the weight 2 to the power of 0 onto the pan, and here we must place it to the left hand side because the right hand side can't be heavier. Therefore, this is nothing but 1, and therefore we end up with the solution that the number of ways to place these weights here, which is f of n, is equal to the product of the first n odd numbers. And therefore we are done.